All right, so we are back and better than ever. We are talking about operations with vectors in space. Wait a second, what am I thinking? That's operations with vectors in space. Yes, okay. All right, so the good news is that operations with vectors in space or in 3 dimensions, the same rules apply as in within 2 dimensions. But we do need to make sure that we understand that in 3 or in 2 dimensions, there is one rule of solving vector equations that is not the same as solving regular equations, and that is we cannot divide a vector by anything. Okay, we can't break a vector into 2 parts. Now we can multiply and make the vector shorter, but we can't divide it into 2 different parts. So when we're faced with 2x equals a, x equals 1/2 a is correct, and a over 2 is not correct because the division has no meaning in vector algebra. And that's summarized right here in this rule. So let's take her out for a spin, try a couple. We're going to solve for vector x. So let's see, I would get 3x is equal to s plus r. And I'm tempted to divide by 3, but we're not allowed to do that. So we are going to multiply by the reciprocal of the coefficients. Of course, I have to do that for both sides of the equation. And what do I end up with? I get vector x is equal to 1/3 times the vector s plus r. Okay, let's do b. We get, let's see, negative 2x is equal to vector d minus vector c. Vectors in space! Okay, and we're going to multiply both sides by negative 1/2. So let's see, no, I don't want that. Let's see, negative 1/2 times negative 2x, let's see, times negative 1/2, just squeeze it in there. Okay, and what do we get? We get, divide that up so it's not confusing, negative 1/2 times negative 2 is positive 1, so vector x is equal to negative 1/2 times vector d minus vector c. We could multiply through by the negative if we didn't want to deal with the negative. This is a perfectly good answer, but if we don't want to have a negative for our coefficient there, we can just simply negate everything, and this is true as well. Okay, last example here. No, it's not the last example, second to last example. If a equals negative 132, find the magnitude of 2a. Well, 2a is equal to 2 times every one of the components, negative 1, 6, and 4. So therefore, the magnitude of 2a is equal to the square root of the sum of each of these squared. So negative 1 squared is 1, 6 squared is 36, 4 squared is 16. Okay, so that is equal to, let's see, 36. Oh, wait a second. I know what I did wrong. That's not negative 1. That is negative 2. So this is a 4. I knew there was something wrong there. Sorry. So 36 plus 4 is 40 plus 16 is 56. So that's square root 56. And that can simplify into the square root of 4 times 14, because 4 times 14 is 56. And the square root of 4 is 2, so that becomes 2 root 14. Now another way is like this. The magnitude of 2 times vector a is equivalent to 2 times the magnitude of a. And the magnitude of a is simpler than this. 2 times the square root, now we're just using vector a, of negative 1 squared is 1, plus 3 squared is 9, plus 2 squared is 4. So we get to root 14 a little quicker than we did over here. Now it's time for the last example. Okay, So find the coordinates of C right here and D. One thing that they don't say that they should is the distance between consecutive points is the same. A to B is equal to B to C is equal to C to D. So we're going to find vector C here. Okay, and to find vector C, I want you to consider some origin. Maybe it's right here. And here is vector OC. Well, wouldn't you agree that vector OC is equal to vector OA plus vector AC? Let's write that down. Vector OC is equal to vector OA plus vector AC. No big whoop right there. Which is also equal to OA plus, well, B is halfway between. A to B is the same as from B to C, so it's 2 times vector AB. And you might be saying, well, why are you doing that? Well, I'm doing that because I don't know anything about point C. So I wouldn't be able to add these. I don't have the coordinates, but I do know the vector AB, because the vector AB is equal to -1 minus a -2 is a +1. -2 minus a -5 becomes 3. 2 minus 3 is -1. So that's the vector AB. And the vector OA, remember, O is the origin, so it has coordinates 0, 0, 0. So OA is easy. OA is equal to -2, -5, 3, the same as its coordinates. Okay. So then OC is equal to, let's see, OA is -2, -5, and 3. Plus 2 times AB. Well, AB is right here. AB is 1, 3, -1. So 2 times that is going to be 2, 6, -2. Right? So that means that OC finally is equal to 0, 1, 1, if we combine those. Now that's the vector OC. It asks for the coordinates of C. Since it's emanating from the origin, this vector, then the coordinates are the same as the components of the vector. So C is at 0, 1, 1. Okay. So now let's look for point D. We'll do that down here. We'll work down here. Okay, let me erase all this here. I'm going to keep that origin though. That's a nice little tool to have. So this is the origin O. Let's just say it's right here. Okay, and let's see, what can we do here? Well, let's again draw vector OD. Okay, and I think you will agree that vector OD is equivalent to vector OA plus 3AB. Well, we've got all this, don't we? We've got OA already. Where's OA? It's equal to, this is OD, I guess I should keep writing this, is equal to -2, -5, and 3 plus 3 times AB. Where's vector AB? Here it is. 3 times all of this gives me 3, 9, -3. Which becomes -2, 3. So that's going to be 1, 4, and 0. Okay, so vector OD is equal to 1, 4, 0. And that implies, since it's emanating from the origin, that the vector OD, the point D, has those same coordinates. So that would be 1, 4, 0. Vectors in space! Okay, I am done. Thank you for your attention. Becker is out.